What happens when you multiply a vector by a scalar? We're going to need to do just that when we get to Newton's second law of motion, so let's investigate. Suppose we have some vector A, and we multiply A by a scalar, a number, let's say 1.5, for instance. Turns out if I multiply the vector A by the number, the scalar 1.5, what I get is a new vector. Let's call it B. So B equals 1.5 times A. 1.5 is that scalar right there. And what we see is that this scalar effectively scales up vector A. It takes that original vector and makes it 1.5 times longer. So if the magnitude of A was originally 10, then the magnitude of B is now 15. Furthermore, scaling it up by this factor doesn't alter the direction of A. A and B are parallel to each other. And so we can see that this triangle here and this triangle are two right triangles. If A and B are parallel to each other, then these two angles here are also equal, and we see that we've got similar triangles. Scalar multiplication produces a couple of similar triangles right here. And so that implies what we can easily verify by counting boxes here. If this side length is 1.5 times bigger than this magnitude here, then the components of B are also 1.5 times bigger than the components of A. So Bx right here, you can easily show that that is 12 units long, 1.5 times 8, and By here is then 9 units long, 1.5 times 6. So in summary, scalar multiplication of a vector. If a vector B equals some scalar S times vector A, then that implies the following. B will be parallel to A. Those two vectors are parallel to each other, just scaled differently, different length, different magnitudes, but parallel, same direction. The x component of B will be S times the x component of A. The y component of B will be S times the y component of A. And then the magnitude of B will be the absolute value of S times the magnitude of A. Now, I had to say absolute value right here because it may have already occurred to you that what happens if S is a negative number. That's also what this little caveat up here is referring to. So, what if S is less than 0? Let's investigate that. Suppose we've got this original vector A now here with x component negative 6, y component plus 10, and a magnitude that's about 11.7. What if we construct a new vector B by taking A and multiplying it by a negative number, let's say negative 0.5? What then happens? What does vector B look like? Well, these rules here will still apply. Bx will be negative 0.5 times Ax, and By will be negative 0.5 times Ay, and B will be 0.5 times A. So you see, B is going to be a vector of magnitude half the size of A, and the components are also reduced by half, but then flipped, a negative 0.5 and a negative 0.5. So Bx, let's start drawing B here. If Ax is negative 6, then Bx will be plus 3. Bx is plus 3, because negative 0.5 times negative 6 gives us plus 3. If Ay was 10, then By is negative 0.5 times 10, so By is negative 5. Let's go down 5. By is negative 5. And with those components, we can now draw in B. Those are the legs of our right triangle. We can draw in the hypotenuse. B goes to the right and down. So there is our vector B right there. That is negative 0.5 times vector A. You can verify that its magnitude here is half the magnitude of A. So the magnitude of B, that'll be about 5.8. And we see what's happened to A by multiplying it by a negative scalar. We have flipped it. Multiplying by a negative number flips the direction of your vector. And also rescales it. So the 0.5 has rescaled it, has shrunken it, but the negative has flipped it. So in summary, we have these rules, or these results when we multiply a vector by a scalar. If that scalar happens to be negative, then instead of B being parallel to A, we say B is anti-parallel to A. They are in opposite directions. We call that anti-parallel. So example, if you have just B equals minus A, then here the scalar there is minus 1, S is minus 1 hidden there, then A and B would just look like this. A and B would be the same magnitude, but just opposites of each other.